Welcome everyone to our new episode of Whiteboard series. I'm Ilya, co-founder of Near, and I have Kostas, chief cryptographer at Mysten Labs and previously at Facebook.
Yeah.
And today we're going to be diving in at all the things that Mysten Lab is working on.
Thank you, Ilya. So, by the way, yeah, I'm also coming from Facebook as the whole founders team, 5 of us. We used to be leaders there. I was leading the cryptography part. Obviously, while Libra was collapsing, I was actually dealing with other stuff, including WhatsApp security and cryptography. And eventually we all left and we built like Sui. And after a year now, almost a year, we recently launched testnet. We had devnet for a while. We're doing really well on testnet. We have wave 1 now running. And yeah, any question that I can answer, I'm open for you.
Sure, yeah.
Yeah.
So, I mean, let's dive in how Sui is structured, and
Yeah.
then we can dive in, right?
Of course. So obviously we all know the basic paradigm of how blockchains are built, right? You have transactions that are reaching some blocks. Eventually you're waiting until either some time or until you have enough transactions here. You're going through some consensus. And then these transactions via some hashing, and obviously someone will pick the transaction that will go into this block, either by mining or by some proof of stake or any other method. You will create a different block with different transactions and they come here. And then we said, okay, cool. This was pretty much the model that we used to have at Libra. And most of the blockchains are built under this like pretty much the same construction. But we said there are a few opportunities where we don't need to wait for blocks. Maybe we can have some parallelization native into the system. And in fact, you can still evolve into a block situation, but before you build a block, you might have other structures that you can avoid all of this blocking until you get enough transactions. And maybe you cannot parallelize because now you need some sequencing here. Right? All of the transactions should go with some order. And we said, okay, we can avoid it. So Sui took a very different approach of actually combining two schemes, two mechanisms, to have all of this agreement on the transactions. And now we have transactions that can actually fly independently and on parallel, TX1, TX2, and TX3. We don't need consensus. You go through the validator set. We are delegated proof of stake. Which means that people can actually give their, with some weight, their stake to someone else who will vote on behalf of them, like regular democracy. And these transactions will go on parallel into a... you're having questions about democracy.
Yeah, regular democracy is a very broad definition, but,
yeah, okay,
but off topic from this, yeah.
I get it. Let's assume there is a set of validators. There are epochs, of course, like every few moments. At the moment, we have a day for an epoch at Sui. This can be rotated based on the stake. And let's assume now that we are in an epoch and we have all of these transactions happening on parallel. And what will happen? In this particular case, I will assume like a 4 of 5 situation. You just go on this transaction to the validators and you ask a signature on parallel from all of the 4 out of 5. Let's assume it's literally 5 and you need 4 out of 5 for BFT. You get a signature back. And then this might be enough if you can construct now the user, the difference between the other chains and Sui. The user here is actually getting the transaction getting the signatures for this transaction. They are forming a certificate and they are sending it back to the validators. How does this help you? Do you understand why this is actually useful?
Well, it's non-blocking, right? So you don't block on waiting for all the stuff, and it's from the user perspective, so you can order your transactions in the way you want. Exactly.
So there is a benefit here in the sense that these validators do not need to interact between them, which usually introduces an n square, or depending on the protocol, it might be n cube, like communication cost. Now, what we did is we have the user, and the user is actually the driver of, yeah, I'm sending a transaction, I'm going into the validators, getting only signatures. They don't communicate between them.
Yep.
Then I receive all of the signatures back. We're using BLS. And BLS, in this particular case, can actually aggregate the signature. The signature is aggregated on the user side, and I send it back to the validators. So the validators, they see a signature of like n 2f plus 1 of them, and they say, okay, if other people also sign, and I also sign, we have 2f plus 1, I can accept this transaction without communicating with them. It's instead of having the validators actually communicating, you have the user being the aggregator, and in this two-step process, which can happen on parallel, of course, you can actually have the same thing as a consensus mechanism. This is taken from a protocol that George Danezis and some other people in our company, Alberto as well, have created back at Facebook. It was called Fast Pay. So this is a method for fast payments without full consensus. There is no full consensus here. And you can have parallel transactions. Obviously, there is a caveat here, right? I mean, you cannot do it for everything.
Well, you don't have ordering.
Yes, exactly. Now you don't care about the order. What are some examples that this works? Can you give me a few applications where you don't need ordering?
Well, given you're calling it pay, probably you mean payment.
Yeah, you're right. Okay, so you go to Starbucks. And by the time you go there, you buy a coffee. And then, obviously, they're ready to prepare your coffee to serve you. They don't need to wait for a block. You just send the signatures, the request signature to the validators. You don't need to wait 3, 5, 10 seconds until a block is formed. And you are getting these signatures by yourself, and you are giving them directly to Starbucks. And Starbucks knows that this certificate will one day go to a block. Now they can serve you the coffee.
So what happens if you don't have the money on your balance?
Well, it's your objects, right?
Yeah.
I will explain how the object models work. But at this time, I mean, you can get the certificate. Starbucks will check the signatures. But the validators, when they sign the transaction, they check that you had the balance to actually pay for this element. And because in order to sign, obviously, they check the correctness of the transaction. But this is what they do. They didn't communicate with other validators. That's the trick. They do the execution, they do the locking of the objects, and they check that you have enough balance to pay for this.
So there is a state transition that happens when you receive the kind of transaction first time. You have changed the state somehow here.
Yes, exactly. There is a state change, but the small difference between other account-based systems and our system were somewhere between account-based and UTXO-based.
Yeah.
So Sui is not UTXO-based like completely. It's not even an account-based. Well, you have an account. So we can, let's finish with this stuff, and then I can explain why the object model, in our case, is very useful for FastPay. FastPay wouldn't work in a purely account-based system of Ethereum, for example. The idea is that you have, imagine this transaction is using only one UTXO. This might be the object that I'm sending you. It might be $5, right? It's these $5 that will change state, of course, and what's the change of the state? I'm changing the owner. I'm just sending you a particular object. So imagine all of them as being like NFTs. Yes, but it's fungible now, right? It can be fungible. It can be mutated. But it doesn't matter. It has an owner. So the balances are not under accounts anymore and are not under contract like internal data structures. They live independently. So I'm sending you this, and this is why I can make the state change without affecting anything else on the network. I'm only affecting the state of this particular object. And this is how you are getting all of this benefit on payments. Some other examples that are very interesting. OK, let's go and list them, right? Payments. Obviously, you can have confidential payments, because there is no huge difference between sending real, visible integers or sending Pedersen commitments. Right? I mean, you can do whatever you want. These can also be objects. What you can do is you can even build your personal web page. It's something that you own. Every single time you're mutating your page, nobody else is affected. If you know how to do your ordering by yourself, it can be on parallel. You don't need blocks anymore. The same thing is for Twitter. We have this example on Sui. We call it Twitter. What is a tweet? It's an NFT. So in practice, when I'm sending something to you, I'm creating an NFT, and I'm sending it to the network. I'm the owner. Then in this NFT, I might even have a reference if it's a retweet, if it's a like, or it's something else. And in practice, everything lives as an NFT. In theory, you can imagine Sui as, yes, we have DeFi, we have the NFT world, we have all of this history, and we learn from the goods and bad things of the past. And we build a system where everything can be considered an NFT.
Yeah, it's just It's an object store, right? Where every single thing has an owner, which can mutate it.
Exactly. And anything that you can imagine, that it's objects that you control, nobody else can touch, it's only you that actually can define the order, can be built with this fast pay model. Some other examples are even things that you cannot imagine it is possible to do with single owner. We call them single owner objects because they have a single owner. Can you imagine of something that you believe that it would require some locking, but I can avoid it?
Well, I think the most interesting is Uniswap.
Uniswap you cannot do. You got me here. Okay, so with Uniswap and the transactions for which you need some people actually to agree
on the order,
on some ordering, you can do different things. One is, in this one transaction, you can probably have a transaction that gets two transactions as an input. We both sign this transaction, and we submit the transaction. So we agreed on the ordering together beforehand. There is an issue here, however, in some applications it might be tolerable that the other player might at the same time send the same object that they locked in the same transaction somewhere else, and there might be an equivocation. So there is a race. Will this succeed, or the other transaction will succeed? And there is another race. Maybe this transaction will succeed on 50% of the validators, and the other on the other 50. And then you have a problem.
So you will need never to resolve.
You need to resolve it. And then the resolution, I guess you're going to ask, how do you resolve this, right? The resolution can happen, even the same user can do a mistake without an atomic swap. I'm trying to send an object. For some reason, I have two services that are running on parallel. I have two servers.
And you're sending the same object to different
You're sending the same object. So what we can do is we're resolving this at the epoch level. At the epoch level, you can do it. And there is, because at the epoch level, you can actually say, if you didn't receive, the transactions can actually define the epoch that they want to be executed. If you didn't receive it on time, just throw it, and then you can start again.
What's your epoch length?
At the moment, it's 1 day. Well, this is something that we will play with that. But there is an extra proposal. Lefteris Kostas, who is one of the, he's a great author on consensus schemes. He's working on unfreezing, I can provide an evidence, right? I have a transaction that has 50% of signatures and the same object another 50%. Unlock it. I provided an evidence, so you can do it. So there is a fast unfreeze. But it's not only those examples that I explained here. There are more examples. Well, DeFi, as you said, Uniswap is more complicated. You can do it with this way, however, with a multi-agent transaction. We're working on the multi-agent. It's not there yet. But there is also lotteries. Imagine if we have a giveaway where in this giveaway you have a car, right? You're giving away a car. People are participating. And obviously, if you imagine a lottery in your head, you will say, no, this requires a third object. I mean, we cannot participate in the same lottery where people are locking money. This money should go to some counter, to some balance that it always goes up and up and up. There is a way to avoid it. And the way to avoid it is I can buy tickets independently on parallel. I pay $5. In this payment, I pay the owner of the giveaway. Let's say it's an organization. So I pay $5 to buy a ticket. Independently, we all pay $5. There is no limit, right? Because the total profit, eventually the reward, is not dependent on the ticket, on the number of tickets. It's only a car. You will win a car. Which means that you buy tickets independently. And in this particular case, you can have the fast pay approach. I just buy tickets. But how is the winner defined? Now I have the problem. You need to define a winner. So the winner can be defined by the fact that you can use fraud proofs. We can use do you know Algorand's sortition algorithm where they do the leader election thing? So very quickly, let's assume that we find a way to have the lottery beacon. I will erase this if that's okay. So we're now on the lottery example, right? And in this lottery example, we're a lottery. We have NFTs, which are the tickets. Ticket 1, ticket 2, blah, blah, ticket N. Eventually on some, we define when this ticket issuing will finish. Let's assume epoch 7. Epoch 7. You start from epoch 1 until epoch 7, you can buy tickets. That's fine. And then eventually you have a list of tickets. And let's assume on epoch 8, we have the beacon. The beacon is defined on epoch 8. How do we define the, I mean, all of them are independent. Right? You don't know, you cannot even sort them, you cannot do anything. However, the users can have access on these tickets because it's a blockchain. They can go offline, they can, let's assume that it's a very basic function of hash of a beacon, comma ticket. Everyone is producing the hash of the beacon, comma ticket, and the smallest one wins. Like the hash that starts with many zeros wins. So only the winner is the one that will go and have a shared object now. Yeah. All of the tickets, 99.999% of the transactions are fast pay, and only the winner will use the shared object, something for which you need consensus. And what the winner will do, will say, I won. You will wait. If nobody complains, you won. If someone comes to you, it's like Arbitrum.
Yeah, then you keep going down.
Yes, you keep going down until there is only one winner, nobody complains, and then you're definitely the winner, or the winner didn't report it. But everyone can report it, right? Even if you are not the winner, you know how to provide the ticket as evidence, as a fraud proof. And this is very similar. Actually, it's a good way to have fraud proofs on Sui. Not necessarily a fraud proof by executing the whole state. It's a special case fraud proof. There are more applications.
So how does the consensus in like
the beacon?
Are you just saying that you're waiting for another epoch for everyone to present and whoever is the smallest?
Yes, let's assume we're using DRAND, right? Or any beacon.
Yeah.
And we say on epoch 8 there will be some random beacon.
Yes.
You don't know it by the time you registered because you registered until 7. So when this beacon is published, now we're going to do all of the hashes offline and the winner will just report it.
But that's what I'm saying. Like, I mean, there's some code somewhere that will be then reassigning the ownership of the car, for example, after this is all published.
True.
Right? So how's that?
Exactly. So at the very beginning,
I'm just publishing an object of this hash, right?
It's a great question. At the very beginning, the organizer defined the shared object. This is an object now that is not single owned. Yeah. It's like a data structure, or it's something that the organizer actually has sent one car NFT here. Yeah. And obviously the rules, like on epoch 8, we have to get the beacon, and if someone executes a transaction, we have to wait, I don't know, for 2 epochs for the fraud proof. So this one, it's a shared object created at the initiation of the lottery. Yeah. Yes. And then the winner will come to this object to request the car.
So what's the interaction when I am like, because for me this transaction is my object, right?
It's just an input.
It's
just an input to the to this particular.
So I mean, here you were explaining how you interact with your object. So how you interact with somebody else's object?
Okay, that's great. So a nice thing by using object-based like model for Sui is smart contracts can get as inputs objects from other smart contracts. Now you can literally have, I'm raising this now, you can literally have an object that is having a reference to another object, or a function under the lottery contract. You have a function that takes as an input some object type X. And this one might be your ticket. So you will provide the ticket. This ticket type can only be created by this smart contract. You cannot create it by another smart contract. So the winner will just send to this function that lives under the shared object an object that has been created somewhere else. I mean, where you're buying tickets. And it can understand that this is object type X, and it knows, oh, it's definitely a ticket that I issued. It was issued by my particular smart contract. So I accept it.
So let's say this lottery contract has, like, you know, function by ticket, right?
Yeah. And this is single owner.
Which outputs
a ticket.
The ticket of that type.
Exactly.
And so ticket has, you know, the owner field, which will be assigned.
Yeah, and probably the lottery ID. There might be a lottery ID as well. Sure. So you know this is a ticket for this lottery, right? Yeah. Maybe you need it.
Well, if it's multi-lottery.
Yes, if it's a multi-lottery one. And I will explain why multi-lottery is possible on Sui. Easier than Ethereum.
And so then when you present this here, right, it then does a hashing with the beacon.
Exactly.
And this like let's this ticket ID.
Yes.
And
if it's smaller than the previously smallest one,
Yeah.
you register it and you wait until the fraud proof expires.
And so
The
you
proof
still need
period.
another method, which is like, you know, actually
Declare winner or something.
like distribute or whatever.
Exactly.
Okay. And so distribute returns the car in this case
To the winner.
to the winner.
Yeah. So as you can see, there are protocols indeed or applications where we can use just fast pay, payments, Twitter, like mass NFT minting. You're minting NFTs on parallel. I mean, nothing is stopping you from ordering your own minting.
But you like, let's say, I mean, it's an object that mints NFTs too, right? Like
Yeah.
in this case, it's buy a ticket, it'll be an object. So
No,
I
no.
can in parallel.
This function mints NFT,
Yeah. So
but you can call it as a single node. I mean, you are not touching anything on this state of
no,
this.
so that's the question is like,
No, you
when I
don't.
write the code for this object, right? I just specify that this is not.
This buy ticket could even live outside this object.
Okay.
In this module. It can accept any module type here. That's why we have the composability in Sui that you cannot easily get on Ethereum. On Ethereum, everything is a U256. How do you know it's a hash? How do you know it's a number? How other contracts know the type that you represent internally in your own contract? While in our case, they are like strictly typed. You know exactly what this is like of this type. And if you also need to use some like generics, we also have this object type T. You know it's from this lottery. And this is why we allow this composability. And I guess one example that you will see with Sui is people who are running independent contracts, then I can go and create a new contract that take as input some object that you created on your own contract. And maybe you can define like many complex structures here of different contracts communicating with other contracts and different types of objects. And evolution. You can even evolve now. If you don't like your contract anymore, you can just create another contract that takes as inputs types of your previous contract. And you know exactly the type of the expected like inputs to the function. So that's a benefit. I think is it clear, at least
Yeah, so I
on
think,
the high level?
Yeah, I think probably worth saying pretty much that the object that's stored on kind of on chain, right? Which are, you know, there's owner kind of and some there's some global ID, I'm assuming, right?
Yeah.
That's used. And then the code is living separately.
Yes.
And the code, can refer to any of the object types.
Exactly.
Right, and so through that only
Which
those
might
types
be
can-
single owner or like shared owner. What is a shared ownership,
Yeah, what
right?
is a
What is a
shared
shared ownership? Okay. I'm erasing this again. And so
I think,
you have a contract on Ethereum. Let's take a contract on Ethereum. You have some, like, what is the name for struct on Ethereum? We use struct, but anyway, you have a contract. This contract has internally usually a map, right, where you have the owner, comma, some whatever is the UID or something, whatever it is. You have a map. This one, because everyone can go and write on this one, it's a shared object, of course.
Yeah.
Right, and it's actually held as like some data structure internally to the smart contract.
Yes,
If it belongs to the smart contract, with high probability, it will be a shared object. But now you can even have objects that do not live as a shared like data structure. It's like a single thing. You have an NFT that has as ownership a user. It's still coded inside this module, but it's not part of some data structure. And this is where you're getting all of this single owner and those that are not single owner. So everything that you see in an Ethereum smart contract where it's usually a map of things, everyone can go there and write, these are the shared objects. And anything else is
But
like
how let's say this is owned by some user, but a third user wants to modify it.
They cannot.
So, but let's say there's a...
How? Give me an example.
We play in a video game, I'm doing damage to your character. The smart contract would modify the health points on your
If
NFT.
you need to access it, you need to go to the shared object model. If you need to modify it without me giving you the permission, you need to use this. But not all of the games are requiring all of this, right?
I'm just
but if
saying
you
this
require
is,
this property, I do agree with you, you need full consensus. You need to go through a shared object, and maybe you can find a pattern. Like, I don't want to be like blind here on the sense that when we say something, it's only possible with shared objects.
Yeah.
Because you've seen before in the lottery,
yeah, you can turn things
maybe
around, yeah.
you can define a model where you can literally do some updates in my character. Maybe you have my character.
Well, yeah, you can have another object which
references this character.
Which is a game game object which has like how much HP you deal, etc.
Exactly.
Yeah,
or you might even have an escrow, which is a game engine.
Yeah, where you deposit. Deposit the NFT.
The game studio is actually having all of the mutable stuff, and then you're doing all of the things that they cannot touch.
Yeah.
So that's the idea.
But this is like, so in module there is internal, like you can have internal data for the module. Okay.
We have vectors now. We're going to introduce even limits on how big these objects can be.
Yeah.
Generally, we don't want to allow like huge objects on Ethereum because they have the hash, the references. They can do whatever they want with the sizes. But in our cases, because you can actually remove things from this object, you can create like very interesting data structures. Maybe you can even have a map, and this map gets up to n elements. And if you need more, you're just creating an extension object on this that can move on, or you can even have a tree structure. So you have pointers, and you're creating multiple objects that are owned by this object. And now that I mentioned this, we have the concept of parent and children. So you can have an object that owns other objects. So when we say this NFT is owned by the user, it might be owned by an object, and this object might be owned by the user. So you can have all of this like inherent structure of some ownership.
So if I modify this, let's say there is this structure, right? There's another object like health points object is owned by this NFT by a user. I can modify this.
Yes, you as the user need to provide all of the path.
Okay, you provide the path,
and it knows that eventually this signature is required.
Okay, so in the transaction,
in the
provide
transaction,
the full path.
Yeah.
Okay.
There is a way. Actually, it was a good question. There is a way to provide the parent object now, and actually it can resolve all of the children object or the children that you want internally to the execution. Maybe you say.
But that's expensive now.
It can be a bit. Well, it depends. Maybe you can find good ways to do it, like some prefixes or some references internally. You just need a byte, and you know that if you see this byte, it's this object ID. Don't provide the whole object ID. And yeah, this concept actually exists. It's very useful, actually. I can explain why it's useful. Imagine you have an account now in Ethereum, and this account owns NFTs in multiple smart contracts. You're a company, and eventually you want to sell your company to another bigger company. What do? You
use near, and you use near, and accounts actually transferable.
Yeah, of course. Yeah, you can do it, but on Ethereum you cannot do this, right?
You cannot. If you did not set it up in the right way,
So pretty much like you, and in our case, what you can do is you can have a main object or multiple objects, and you just store all of the ownership under this object, and you just change the ownership of this particular parent object.
On Ethereum you would do the same. You would have a smart contract, and then you would. This will be the.
Yes, but now all of these have literally types, right? You can do whatever you want now. Because if you have a smart contract on Ethereum, maybe you don't have the ability to have all of this abstraction and put whatever you want there. Here, you literally can put anything as a children, as a child.
You kind of can, but yeah.
Yeah.
On Near, you can actually swap this. The account itself is a contract.
Yeah, but you cannot have parallelization because of this.
Well, you parallelize on account level. Every account is independent.
I agree, but you have to split your account logically. You need to split your account logically. You cannot, now because you can change it, you cannot have the fast pay model, obviously, because imagine in one transaction you are changing the account, and in the other you are doing a transfer. You need to have the order on who is the owner at the time of transaction.
You need to synchronize on
exactly. We don't have this ability because of parallelization. So obviously you lose something and you get something. But we're working on it, by the way. There might be solutions for this as well.
So I guess just to go back a little bit to this.
Yeah.
So when I'm changing the state of this, right? You're saying this will wait until end of the ebook, like to.
No, if you change if you change the state, and it's a shared object, you will not get the fast pay path.
But that's
you have we have consensus.
Okay. Okay.
So let's go to this now. Right, because we only mentioned one type of the consensus. It's not full consensus, but a way of like,
it's like a
broadcasting.
It's a pre-commit,
exactly. So what is the life cycle of a transaction, right? I only explained like part of it. So we have a transaction, and this transaction will go first, like let's assume in the fast pay world, where the validators will give you 2f+1 signatures, and this is like for locking the objects, because here you will have object inputs, object 1, object 2, blah, blah, blah. So you're locking this, actually you're getting all of these signatures back, that the validators say, I lock this object. And then you return back the certificate. This is a certificate now. You are the aggregator. You're the aggregator. You send this back. And then the validators again will provide a 2f+1 signature. I executed it. And this, if it's fast pay, right? If it's fast pay, it will go through this model. And this certificate of the certificate after the execution, that's the effect certificate. It's enough to go to anyone and pay you. But if it's not fast pay, then after the locking mechanism, after this one round trip, you can actually send it to Narwhal and Bullshark. And this is literally a BFT consensus, like one of the fastest. This one doesn't even require a leader election. So previously, if you see all of our documents, we had task. And then it's pretty much the same team that actually created both tasks and Bullshark. But task requires some random beacon for fairness and other things. And Bullshark, it can help if you have a random beacon, but it's not a huge requirement here. And now you're not going through fast pay, now you're going through this. And here you have to wait for a block. And after you have these blocks, obviously you have, some are with effect certificates, some are with Narwhal. What do you do? We have another model where these fast pay executed transaction, they can also go through a Narwhal eventually. And all of these Narwhals now, this and this Narwhal, they go through the checkpoints. And this is the part where Sui is a blockchain. Checkpoints evolve into
pretty much blocks.
Yes, but these are enough as evidences for I don't know, if you have a delivery versus payment, you see the payment and you deliver the object.
How frequently are the checkpoints?
So we're working on the checkpoints. It might be seconds. I think we had an example with 6 to 10 seconds, if I remember correctly. I don't know what the number will be on mainnet, because now we're working on
synchronizing
this part on synchronizing to a checkpoint. And
how long does this actually usually take? Like getting certificate and certificate?
This happens on parallel. Don't forget that the user
No, I know, but it's still latency, right? Like
it's
two
round trips.
Yeah.
2 round trips on parallel.
So like a second?
It's less. I mean, it can be like usually it's the worst case. It's 250 milliseconds or something. Yes, you can get it in half a second.
Okay.
Obviously, it depends on topology and other things here, right? But in theory, you can do it. But you can, and it can happen on parallel. There is a huge benefit with. I mean, if we get this route, this is like horizontally parallelizable. What does this mean, right? Unlike other blockchains, exactly. We can just build workers. And actually, there are workers on Algorand and Bullshark anyway. But this is for extra optimization here on the consensus scheme. This is
so I will want to go deeper into this, but let's.
But this one is actually Narwhal. Is the mempool. And we have mempool, and this mempool is actually pluggable and can work with both Task and Bullshark. And we've seen some companies actually using this for other, I don't know, their own systems. But yeah, that's the whole idea. George is the best person actually to ask all of these questions. I can go a bit deeper.
I mean, I think high level would be probably good to highlight this because
you have workers here, right? I mean, you can have workers, and it is possible that they put Narwhal packets that they
so Narwhal. So let's say you have all these validators, right?
Yes.
So you assign some of them to be so the transaction comes in.
Yes.
But
all of them, they are forming different let's say blocks, small blocks. And it is possible that one block is having, this block is having TX1, this also has TX1, they have different blocks. And then they're starting proposing this. And if you see a transaction that was already included in a different block, I mean, it was already included. There is some duplication here, but this is what gives you the speed, right? I mean, some transactions are indeed in different blocks. However, it doesn't really matter, right? You just need one of them to include it. And it's a DAG. You get a DAG in Bullshark, and eventually you have, I don't know, multiple objects, multiple blocks being proposed. Some of them might be overlapped, not fully overlapped. And then you go back to check if like a transaction was already included, you don't include it. We have some hash maps internally and all of this.
So like, will every node need to receive blocks from everybody else?
All of them can actually propose blocks.
Well, they propose, but then they will need to receive it to identify if it was included.
Yes, you need 2f+1 signatures, right?
Yeah.
If you receive 2f+, even if you didn't receive something, but you receive an evidence that 2f+1 have signed it, you accept it.
Yeah.
That's the idea. Well, you will see a few systems that actually are down and only 2f+1 are live.
Yeah.
Eventually, you need to sync up.
Yeah.
You have 2f+1 signatures. You assume that the system is running correctly, assuming the BFT property holds. But all of them can propose. That's the thing. And there is a difference because it's a DAG. MEV is slightly different on how you do on DAGs. You know the story, right? It's more complicated.
Yeah, let's not go. MEV is a whole separate. I'm just like, just so for clarity, right? So let's say I am as a user, right? In this case, like, because I already have the certificate that they saw the transaction.
If you go through, yes, you
well,
have this.
Like even if
this is a lock. This is a lock of the object, right?
Even if I'm not going through this.
Okay.
Even if I'm not going through FastPay, I still send the transaction first to all the.
Yeah, the first one to get the transaction that I locked the objects for now. Yes, you are sending it, even to Narwhal.
Yeah, and so
to
like,
whom?
I send it to everyone, or
you can send to some of them. You don't need to send to everyone.
And so they propagate it with blocks, right?
Yes.
And so that's part of Narwhal, the propagation of blocks, and the Bullshark is a way to resolve all of this into the.
Exactly. In theory, you can even send it to one, but you have the risk that this one will not forward it. So you can actually pick a bit more. Like this number, I don't remember if George has a real number. We're testing this number, what it will be. Obviously, if you send it to f+1, it's enough that someone will propose it.
Yeah. Okay, so then everybody proposes a block. They probably, and then they start sending their blocks to the other validators, right? And so I'm from a single validator point, right? I have my block that I proposed, and then I received some other. There's no timestamping, right? So they come all at
the moment
time.
We don't have timestamps. You can have timestamps in theory, so you cannot have timestamps here. It's more difficult.
Yeah.
Because this is on parallel.
They cannot,
but here
you cannot aggregate on a timestamp.
But here you can have timestamps in theory. You can have like the block proposer here to have a timestamp.
Well, but I'm just saying, like, just in general, it doesn't matter at which. Like you receive them at different points of time, right?
Yeah.
So they just point at like what was the last thing they saw.
Yes, exactly.
But they point at all of the things they saw, right? Or what, like how are they determining the referencing?
Well, you have transactions that they refer to previous object versions. We have versions from the objects, and obviously you know where to reference. If this has been signed by 2f+1, it's fine. I mean, you can reference.
Yeah, you can just reference that.
Yes.
Yeah, okay. And so then within here you have like there's transaction 1, it's transaction 1 here. Like at some point you build pretty much an ordering, right, of transactions.
Yeah.
Like how
this is happening, and this is what we're working now in the checkpoint eventually.
Okay, so this is like kind of as this all gets aggregated, then you're like, okay, now we know, like we saw 2f+1 up to here, so we can run this ordering up to this.
Exactly.
And then you keep
accumulating. And the checkpoint can also have a timestamp.
Yeah, well,
and it's up to the application to say, okay, do I trust this time? If we don't have timestamps now here, but we can have here, which is more like fine-grained. There is sequence of blocks. While here in the DAG, it's very difficult to have a good timestamp. But yeah, that's the whole idea of like the basic protocol. What people can understand on this one is definitely you need one round trip to get a locking on the objects, some certificate on the objects, and then you get to two routes.
Why do you need to lock the object if you're going to this?
Oh, this is, I have a feeling, I'm not 100% sure on this, but I have a feeling because we want to actually have one flow independently on if you're going to here or
so
here.
Just it looks the same,
Yeah, it looks the same. The user, I mean, it's as easy as possible for the user. They don't even need to know where they are sending their transaction. This is happening, everything on the background. So that's a general way of how Sui works, right? And we explain a few examples. There is also move in the game.
Yep.
And in move, some of the hints that we gave already is everything is object.
Yep.
Like it's strictly typed. There is also some capabilities, like the object can have capabilities like drop. This is droppable. It has key. It has store. It has. There is another one as well. But all of the idea is when you define an object, you say has dropped, has key, has store, whatever you can actually have on this one. And these are used, copy, I think it's also copy.
So that's a standard runtime level.
Yes, exactly. And if it's a copy, you can copy it. If you're not having like has copy, you cannot even copy it on the code, we will stop you. The same thing is for key, the same thing is for store.
What is key?
Key and store have to do with, is it an NFT, a real NFT, or it's like you have an object that references to another object. It can be a key to another object.
So
and drop if it's droppable.
So user is a key object.
Yeah.
Account is a key
Yeah,
object.
it can be. Yeah. So that's the idea. We have this, let's assume abilities, capabilities.
Well, it's traits, right?
Yeah, well, yeah, it can be
It's
called
a
traits, but it's also abilities that they have. So Sam is working on some very interesting, like even extra, Sam is our CTO, extra things that we might have here, and Todd Nowaki, who's leading like the move team. And there is another thing that we have to know about Sui. So we explained all of this. What we didn't explain is transaction cost, storage, and this kind of stuff. Our tokenomics is very interesting, right? What is usually the cost for a transaction? Why do you pay the validators? Why do you pay gas? For two things, execution and storage, right? You need execution.
Yep.
Yeah. You have questions?
No. I said yes, execution storage.
You pay for this. And also, this is the cost that the validators pay, right? I mean, a validator has to execute transaction, but at the same time, they need hard disks, they need all of this stuff to maintain the network and the state. What we do is we split the gas between these two, and we have a storage fund. What is a storage fund? When you pay for this transaction, let's assume that this is TX cost. Part of this, well, there are some functions from Alonso, our economist, go to a storage fund, and this storage fund is actually giving the opportunity for the users. If in the future you want to delete this NFT, the storage that it takes, you will get some rebuttal.
You get the return, yeah.
Yes, you get some return. And it also gives an advantage to the validators. Are we good with the time? Are we good with the time?
No, we're good. We're
Okay.
still 16.
Okay, cool. And the storage fund is
Reinvested.
yes. And there is a benefit for this, right? Imagine you're a validator and you come 1 year later.
Yeah.
You need to maintain state. You didn't get a thing, right? Even a single cent.
You're not paid for the transaction itself,
Exactly.
but you need to store all the
You
data
have a
of the
storage fund that
contract,
we can pay you.
Yeah.
Obviously, you're not going to get as a user all of this. I mean, if you delete it, you're not getting everything back.
Yeah.
Like the rebuttal is shorter. But at least you're getting something. Some people might use it to have like, I'm storing objects. And then if the market goes up, in practice, I can even make money in theory. But let's assume that this is not the reason. The reason is if your business goes, I mean, you dissolve your business, you can get something back, right? You don't need the NFTs anymore.
Yeah.
Why do you need to pay? So that's another difference. I don't know how you're doing it on NEAR. Do you have a different
Yeah,
model?
so we lock NEAR itself, and if you delete the storage, you get back NEAR.
Okay,
And
I see.
then
But
developers
do you
can.
split it between execution and storage?
So your gas is only execution, and then you pay NEAR for storage.
Oh, I see.
So storage is like, it's called storage staking, but it's very similar to this model.
Okay, so there is a different token for the gas. And
It's not a different
for
token.
NEAR?
It's just it's two parameters pretty much.
It's two parameters. Okay, but this has a price as well, or it's NEAR?
Yeah,
again?
it has a price that fluctuates with like
Okay.
how expensive computation is, and this is fixed price.
Fixed per byte.
Yeah,
I see.
because like storage doesn't change, right? Like
Yeah,
the fact
of
that
course.
more people want to use
Of course,
stuff NEAR
of course.
doesn't change.
So that's another thing that we're doing. There is another like part of Sui
So I mean,
Yeah,
just like
oh,
on the
sorry.
search fund, like,
Yeah.
so this is actually reinvested, or like how is that managed?
So there is some function on how we define all of these parameters in this storage fund. What do you mean by reinvested?
Well, it's like it's just a bunch of Sui sitting in,
Yes.
in some
Just
place.
sits there, and there are some functions giving money to the validators and to the users for rebuttals.
I see.
Because then we might not be solvent if we didn't, right? You can invest it in theory. You can do a lot of things. But this is something that will be defined in the smart contract level, not outside the smart contract, right?
Yeah.
I mean, everything will be transparent if something happens to this one.
Yeah.
But in practice, you need to have all of the money to return back to the users if they delete.
If they want to free everything.
Yes, if they want to free anything. So that's one part. The other thing that is interesting with us is crypto agility. I'm going into my territory now. So what do we have, right? We do have API internally from the STD API on Growth 16. Like we have zero knowledge proofs.
Yeah.
I mean, the smart contracts can literally execute zero knowledge proofs by just calling the Growth 16 verify. Only verification unit on the blockchain. We made like some improvements on ArcWorks. I don't know if you write Rust, you know that there is ArcWorks RS, and this one is okay. It's like the all of the structure of ArcWorks is great, but we made some additions by adding a BLST, which is a BLS library for like faster faster operations on the BLS curve. And now we are like two times more faster than the original ArcWorks. So we have very, very fast verifiers on Growth 16. We also have, obviously, we have the BLS verification even internally to the contracts. We do have, I mean, the regular ECDSA.
Did you speed up BLS?
ECDSA, we're using BLST, but we're working, you will see in a couple of weeks, another optimization on the aggregation on top of the Dan Bonnet paper. We managed to make a way where, because it's validator's keys, if you're using BLS, mostly you need it for validator signatures. What you can do is you can have different ways of aggregating by even avoiding proof of possession of the keys. You might not need proof of possession anymore. Usually you need to prove, because you're doing aggregation, that A, it's my key, to avoid the kind of attack called rogue key attack. So because you're aggregating, somehow I know some other validator's keys, and I create my key in a way that I take advantage of your keys, and then I can omit your signature, and somehow the people will believe you signed. We found some ways to make it a bit faster. So there, we call it SKR. It's multi-signature key randomization. So there is a version of BLS. Let's see if we're going to have it already, because the BLST implementation and the aggregation is really fast now. I think we're the first company that we have a library called Fast Crypto. So this is popular enough now. I mean, even funks are using it. That have the fastest implementation we find in Rust. We make all of the adjustments. Obviously, we use them on Sui, but this one is like published independently, and everyone can use it. We have Growth 16 there, we have BLS, we have ECDSA, we have EDDSA with some improvements, ED 2.5.19. I personally found many attacks on all of the implementations. Like,
great.
Yeah, it's 2 months ago, 3 months, oh, no, it was July, where I think all of the implementations were broken. Could be broken. Could be broken. And there was even Trezor and some other wallets that they had an exposed API where someone, if they were not careful, they could expose a private key. Trezor was lucky and it didn't have the like this vulnerability being exploited. But someone could do it accidentally. Now they fixed it. I mean, they were super fast to fix these things.
And it's in Fast Crypto you have all.
Yes, we have already Fast Crypto, and what we do in Move, so we have Move.
So you provide all that as API.
And in Move, you can have Rust, I mean, libraries, and then obviously you can have binaries, and we execute this as native function in Move now. So we actually implement the algorithms in Rust, and then Move has some like precompilation.
Just exposed, like
and exposes the API. It's all of this, and there is also another about Pedersen commitments. This is for like confidential transactions and other things that you can do. Generally, you will see a very rich API on cryptography. We even have DRAND support, native DRAND support. So literally, you can use their DRAND committee internally to Sui today. We also have some other protocols that we implemented, like some optimistic Satoshi dice for lotteries, even multi-party, so you can even avoid VRFs. We're working on our own VRF.
There's examples, right, on top.
We do have examples. Obviously, we're not providing confidential like payment now, but the functionality is there that if someone has the license to do it, they can do it. So these are like parts of the signatures and like all of the fast crypto part. But we have another thing as well. It's what the user can use to sign. I don't remember if are you crypto agile on what types of signatures people can use?
We have ECDSA and Anderson curve.
ECDSA?
We can add more.
And EDDSA or?
Yeah, and EDDSA.
And EDDSA, okay. So you have these two, eh?
Yeah. But you can add more, like.
Exactly.
Really
and I guess you have K1, right? The Ethereum curve.
Yeah, not the R1.
So we now
people
work on the R1 as well. There is a benefit.
There is benefit, yes.
What is the main benefit?
In the
mobile
devices,
enclaves. Yes, mobile enclaves. So we're having this, and obviously we're making, because they're not good implementation of R1, unfortunately, you will realize it as well. This is faster. This is faster because the Bitcoin world actually made it faster.
Yeah.
And this one is faster because we also contributed on this.
Well, and also generally this one is way faster than.
It is. It is. But even our team actually contributed a lot on making this a lot faster. Even on batch verification, if you go, we even have half aggregation. Here, you can literally aggregate without any interaction in the DSA signatures to half of the size. We published this on RSA conference like 2 years ago, while at Facebook. But yes, R1, and we're going to even have BLS on the user side, because in BLS you can have very efficient threshold schemes without going into this
because
mess of MPC and.
Well, we have a multi-sig implementation for this, but
Is it deterministic?
It is, but it's a painful as.
Yeah, it's painful, exactly. And then we said, okay.
Yeah, BLS just.
Let's use BLS. It's a bit more expensive. By the way, you can see all of the benchmarks in the Fast Crypto library. We even have diagrams. You can see like how they perform.
How it scales,
Sweet points about 42.
It's the answer.
It's 40 times more expensive. So
we were actually planning to use BLS for our validators.
But you have to for validators, yes.
Well, we end up doing this because at that point
for validators you're using
it was too expensive.
How many validators do you have?
Like 100 plus 200.
Okay. Then BLS will perform better. Download Fast Crypto and you can use it. Literally, I mean, we did a lot of good work there to make this as fast as possible to be comparable. But obviously, we have less. Then there is a point to compare between the size of the signature, because the size also plays a role, and the execution cost. And you can do some other batching and parallelization. We also did some parallelization here. So this is one. This is the other part on cryptography, and a very interesting signature scheme is coming. I unfortunately cannot reveal it because we don't have yet the security proof. But this one will be, I think, one of the best ideas in the space on how you can authorize users without smart contracts. So that's the main idea behind Sui. I don't know if you want to ask any other deeper question.
I mean,
can even go to transparency and other things.
We can discuss the transparency.
Okay. So today is the day that that I published something. It's very interesting, right? I mean,
it's going to be published a bit later, right? So
yeah, we will publish it later. But the idea is, I played a big role in the past, personally, as my personal goal. While working at Libra, we had to work with regulators. So I was involved in this meeting sometimes, and I had all of the input from auditors, regulators, like regular auditors, not only governmental auditors. And Libra, literally, it wasn't technical, the issue that didn't work, right? It was other things outside our territory that didn't allow it to be able to be a product. However, we did a lot of work on solvency. We had very good economists, even Dalia from Chainlink now, and Christian Catalini, like the economists that we have now in Sui, Alonso de Cortari, myself as a cryptographer, Lera Nicolaenko, who is now on A16Z, and some other cryptographers like around the world, in Visa Research, in Cornell University, Panos and Jan, we worked a lot on finding, okay, even if we want to have solvency, it's not easy. It's very, very difficult. How you have a centralized exchange, or even a decentralized exchange, if it uses some of the assets outside the blockchain, how do you even verify that what they are liable for, they have the exact same assets or even more, a surplus? And then some companies after FTX started to offer like proof of reserves and proof of liabilities and proof of solvency. So the most common thing is you are putting for liabilities, you are putting all of the user balances as leaves.
Yeah, and then you Merkleize it.
And you Merkleize it, exactly. You are going into...
And then you let users go and check that their balance is there.
What's this? What's the proofs of liabilities? This is a decentralized, probabilistic, random sampling.
Yeah.
That's what it is. We call it proofs of liabilities, but this is exactly what it is.
It's also like you need to rely on users to actually go check, which...
Yes, but even in the regular, there is no other solution. And I can explain to you why there is no other solution. This is for SEX, right? SEX, the centralized exchange, not the other SEX. No, you remember Vitalik's recent post, How to Have a Safe SEX? This was the title, literally. But obviously we mean about like centralized exchanges. The problem is, first they have issues with privacy.
Yeah.
And the other thing, if you have like the values here, 5, 10, 12, I mean, people who do inclusion proofs, they can see the neighbors. If you hide them, you need an auditor. And the auditor can obviously see them, but the users can only check inclusion, and they have to blindly trust the auditor. This is one of the things that we mentioned in like Binance now, but some other exchanges that they're also using the same algorithm, like Kraken and others. And something that they always do, I don't know why people are doing it, is they truncate hashes. So instead of using 32 bytes, they're only using, for example, 8 bytes for leaves. And this is very dangerous. Why it's dangerous? Because someone can now find collisions off-chain. Here you're using also some salt per user. You can just play with the salt until you find 2 balances. You report the lower balance to the auditor. You report the real balance to the user. And the auditor will do the sum and will see some very small value, even 0 in theory. And the user will say, no, my balance was there, but this is completely wrong. And this is, I don't know, I feel the mistake is based on the fact that traditional auditors have implemented the original Maxwell approach. It was Greg Maxwell from the Bitcoin like space, like a great scientist. He didn't propose this, but the first auditor actually did it for UX reasons. They didn't want the people to see, like, imagine you usually present this as a hex, right? And then you see some numbers here, and they say, okay, let's truncate it. But this truncation is actually vulnerable because now
8 bytes is too easy.
8 bytes, and if you go to 4 bytes for a collision attack, this is 2 in the power of 32. I can do it in seconds, like. And we identified this issue. We identified other issues regarding the summation. Vitalik takes now a leading role on trying to propose even a standard. And there is the community, ZK Proof, and many cryptographers that we literally want all of this to be zero knowledge proof.
Yeah, so you don't need to provide the pairs.
Yeah, we do have a paper. It's called DAPL Plus, and actually this year was in the top 10 innovations of 2021 in one of the biggest, I think, innovation contests in the world, CISO. And this one works really well. We've proven security and all of this. Vitalik now is proposing another scheme where instead of using this, let's like snark everything. And by snarking everything, probably we can have faster verification proofs and other things. However this works, in my opinion, we should start with this, at least to ensure that it's better than the current Merkle tree approaches. And I'm like all ears to see Vitalik coming with a real which snark to use. Do we need a trusted setup? Go to the regulators and convince them that we need a trusted setup. There are all of these things that...
with snarks, sadly, it's still
it gets very cold. Yes. While this one is using bulletproofs, it doesn't require a trusted setup. So we say, let's start with this thing. We have proof of liabilities. How do you solve proof of assets? There it's difficult, right? With centralized exchanges that might have liquid, semi-liquid, liquid assets, what do? You need both auditors and oracles.
But also, like, yeah, I mean, they can be like investing, and that's part of the strategy, right? And
Exactly.
That's the whole point.
Investing on-chain is probably traceable, but investing off-chain
most of it is off-chain, right?
Yes. So, and this is where the problem starts. Sometimes, I don't know about the FTX situation, right? I mean, nobody knows the correct number. But the idea is, even if they were, and something was illiquid, in practice, you're not solvent. I mean, if someone tries to withdraw the money, you're not solvent. And it's very tricky how to define solvency.
Yeah, like, well, this is where it is a question of defining some limits
exactly.
and lenders of last resort type thing.
Something that I realized in the past, this was Deloitte, in this particular case. We found attacks on Deloitte as well 2 years ago, right? Very similar attacks that we found now on Binance. Binance, by the way, is super transparent, at least on me, and they told me that they will check everything. They're open, and I give them. I give it to them.
Like,
right?
This is like the scheme.
They just didn't know, right?
Yeah,
it's the auditor offering something, and if you don't have, I don't know, crazy cryptographers in your team, you just accept what the auditor is giving you.
Yeah.
And they said they will fix it, so I feel confident they will do it. But even back then, one of the issues that we have is sometimes synchronicity. How do you synchronize the input you get from the proof of assets with the proof of solvency in the millisecond level? Because you know what can happen? You know there is an audit.
Yeah.
Like a moment ago, you move the assets here, and then you are removing them back again. Or there are in-flight transactions of the user. Right? I mean, you're saying
we need to snapshot at a point.
Yes,
of the
but
block,
let's assume at the time, like 1 millisecond before the like the deadline, I'm sending money, but you will see the transaction on your report whenever the SEC decides. Yeah. And there is a thing, right? They can play in these late moment transactions. They can play, and Deloitte told me that we give a 5%. Usually threshold, because of all of these things that can happen. But we realized that most of them had 1 to 3% surplus, if they were secure. So all of this is happening now. We are trying to, even as Mysten, and I guess all of the other companies will help with their cryptographers, we need a standard. Yeah. Because something that can happen is BitMEX, if I remember correctly, published something literally today, just hours before my announcement on the Binance vulnerabilities, with a different scheme. And then Binance is going to propose a different scheme, and then Vitalik is proposing another one. I say, let's start with this, and we can go to Vitalik. We cannot have 10 solutions, right? It's very important to go with cryptographers, with auditors sitting on the same table, with exchanges, with L1s and people who want to help. It's also proof of assets, as we said. Sit together and have a standard.
Okay.
Yeah.
Sounds good. Well, thank you. I mean, thanks
so much.
For deep dive into Sui, and subscribe, comment, check out the papers and the reports, and we'll see you next time.
Thanks again.